Okay, in this opportunity, now we are talking about precipitation, which is basically a practical application of the solubility equilibria that we've been talking about recently. Okay, so if you remember 170, we were talking about whether you mix two solutions and you obtain a precipitate, which we consider it insoluble. And now with the solubility equilibrium, well, it's not exactly that it's completely insoluble. Part of it will dissolve in water, and then as its heterogeneous equilibrium will be established. Now, how can we use that information to our advantage? Well, it comes with precipitation, being able to predict when precipitation will occur. In the simplest case, just by mixing two solutions in which you can potentially obtain a product that is insoluble, well, basically all you needed at that time is that you will form something that is insoluble. Now, with this concept, now with that we know about solubility, well, it's not so much that just mixing the two solutions will produce a precipitate. Certain conditions have to be met in order to observe that precipitate. So we're bringing the concept of the reaction quotient to the solubility equilibrium. Remember, the reaction quotient will allow you to predict in what direction the equilibrium will shift according to the concentrations that you have at equilibrium. So we can apply the same thing here for solubility equilibrium. Okay? So now that this reaction quotient will have a different meaning, still it's within the context of equilibria, but we are applying this to precipitation. So things to consider here is that if the reaction quotient is equal to the KSP, well, normally you would say that the system is at equilibrium, right? Well, an equilibrium here for precipitation, it means that there will not be precipitation, okay? So the concentrations are such that your system is at equilibrium. It means that you have a saturated solution, but you will not observe precipitation. Now you are very close to that condition. You just have to increase a concentration of one of those things to start precipitation. But at that point, if Q equals the solubility product, there will not be precipitation. The next case is when Q is less than KSP. Now remember, Q equals KSP, you are at equilibrium, there is no precipitation. But in this case, if Q is smaller than KSP, then the solution will be considered unsaturated. Okay? Remember that the meaning of a Q equals to KSP means that the concentration of the products are smaller than they are supposed to be. Okay, if we look at the equilibrium, let's say we have MX, which is a solid that are in equilibrium with, and let's assume that they are monovalent. Okay, if Q is smaller than KSP, which the normal concept that we were associating with that, well, the products are smaller than they are supposed to be, so the equilibrium shifts towards the production of more products, right? So the equilibrium will be shift in that direction, and in that direction you are dissolving more of the solid, so that means there is no precipitation. Okay, in fact, if you are more of the solid, it will dissolve because the concentrations are smaller than they are supposed to be according to the solubility equilibrium. Now things get interesting when you have Q larger than KSP, because a Q larger than KSP means that the concentration of the ions in this case are larger than they are supposed to be according to the equilibrium. And under the normal circumstances for any other equilibrium, that means you are favoring the reactants. Therefore, in this particular case, the equilibrium is shifting to the left, so towards the production of more solid. So this is truly what happens when you produce a precipitate. Okay, So only when Q is larger than KSP, you will observe a precipitate. And remember, for Q, you use any concentration that you are being given. You put it in the expression of KSP, but you are calculating Q because you are not using equilibrium concentrations. There is a special case when you have Q, there is no precipitation unless disturbed. Those are called supersaturated solutions, but we are not gonna mess with that in this case. Okay, we have no prediction power using math. That means, okay, so we're gonna leave the supersaturated solutions out of this discussion because technically they should precipitate, but conditions are such that they are not, and then you have to seed it, meaning add a crystal of the solid, and then it will precipitate. So, but don't worry too much about it. So some of the cases here, precipitation only if Q is larger than KSP, unless you have a supersaturated solution, but I do not worry about supersaturated solution. If you want to learn about supersaturated solutions, you can go to YouTube and look for hot ice. Okay, there are several demonstrations with hot ice, which is basically sodium acetate precipitation from supersaturated solutions. That is more general culture for you, nothing that we're gonna test on the exam or anything. So we are leaving supersaturated solutions out of the content. So how do we predict precipitation then? So here we have two solutions. We have lead nitrate and sodium bromide. So what happens with these solutions when you put it, with these ionic substances when you put it in water? So lead nitrate is gonna do this. Okay, it's gonna separate into ions. And let's go with states. And this is soluble, so I'm gonna add the X form here. Plus 2 nitrates. Okay, if the concentration of lead nitrate is 0.0150, then you produce 1 mole of lead ions per mole of lead nitrate, so the concentration of the ions is also 0.0150, but for nitrate is twice as much, so this is 2 times 0.0150. Okay, and if we look at sodium bromide, then sodium bromide in water will give you sodium ions and bromide. Okay, now the concentration of sodium bromide is 0.00350, which means the concentration of each sodium and bromide is also 0.00350, 0.00350. Now, out of these, all these ions, the ones that we are interested in are lead and bromide, because those are the ones that are going to produce a solid. Okay, out of these two, you obtain lead bromide. Okay, and lead bromide has a KSP. Let me write that better. The KSP is equal to 467 10 to the negative 6. Okay, and the solubility equilibrium for that is lead bromide, which is the solid, in equilibrium with lead ions and 2 bromides. Okay, therefore under these circumstances, Q is equal to the concentration of lead times the concentration of bromide squared. And we are pretty much using the concentrations that we are giving based on the solutions that we started with. So Q is going to be equal to the concentration of lead, 0.0150, times the concentration of bromide, 0.00350 square, and that will give us 184 10 to the negative 7. Okay, so now we compare this value with this value, and we notice that Q is smaller than KSP. And because Q is smaller than KSP, then there is no precipitation. So if you mix these two solutions, 0.0150 moles of molar of lead nitrate and 0.00350 molar of sodium bromide, yes, potentially you obtain something that is insoluble, but nothing is going to precipitate because the concentrations are not large enough to promote the precipitation. So you can have these two solutions mixed together, it's gonna still be clear. There is no precipitation there, okay? Just because Q is smaller than KSP. Now, what if we take these solutions and somehow we concentrate these solutions in such a way that now lead nitrate is 0.060 or 0.0600 molar, and the sodium bromide is 0.0158. We're not writing the equations again, so if you have 0.0600 molar lead nitrate, then it means the concentration of lead is equal to 0.0600. And if you have 0.0158 molar of sodium bromide, that means that the concentration of bromide is equal to 0.0158. Okay? Q is going to be equal to 0.0600 times 0.0158 squared. Okay, remember this is lead, this is bromide. And now in this case, we obtain that Q is equal to 150 10 to the negative 5. Now we compare this versus 467 10 to the negative 6. Okay, this is our KSP. So this is Q, that's KSP. Now Q is larger than KSP. Therefore, the lead bromide will precipitate. Okay, now under these conditions, these concentrated solutions, now the concentrations are high enough that you will observe precipitation. Okay, so this is how, you know, just mixing two solutions in which you obtain insoluble solid doesn't mean that you will actually obtain the solid. It depends on the concentrations that you're starting with. Now, one practical application of this is the concept of selective precipitation. Let's say you have different metals there, usually goes for metals, and then you want to separate them. You can use selective precipitation. What do you need for that? Well, first, those metals have to produce something that is insoluble. Okay, that is not enough. You need to have differences in solubility. Okay, so if you want to precipitate one but not other, then the KSP values have to be significantly different. But this, the real meaning behind this, the solubilities have to be significantly different. The only thing is that the measure that you have for solubility is the KSP. You can calculate the molar solubility, of course, but the concept behind this is that they have to be significantly different in solubility so that you can separate it. If they have the same solubility, you are going to let's write that down. If same solubility, then co-precipitation. What does that mean? They will precipitate at the same time. If you want to separate them, you don't want them to precipitate at the same time. So that's why we are naming it selective precipitation. They have to have different solubilities. Okay? So how can we approach a problem like this? In this case, we have magnesium and calcium, and we have this in seawater, and we want to separate magnesium from calcium. Okay. Now, the equilibriums that we are looking at here is magnesium, because we are using hydroxides, so it's magnesium hydroxide that goes to magnesium ions and hydroxides, and calcium hydroxide that goes to calcium ions, and of course those two hydroxides are insoluble or solids, and the stoichiometry is the same, so we can compare the KSPs directly. Okay, because for magnesium hydroxide the KSP is equal to 206 10 to the negative 3, sorry, 10 to the negative 13, sorry. And for calcium hydroxide, the KSP is equal to 468 10 to the negative 6. Okay, so obviously, given the same stoichiometry, when you look at the values of KSP, magnesium hydroxide is less soluble than calcium hydroxide. Now we're going to focus our attention on magnesium hydroxide. Okay, and we have a starting concentration of magnesium hydroxide. So what we have to do here is that, remember that KSP in that case is going to be the concentration of magnesium ions times the concentration of hydroxides square. We are technically solving for the concentration of hydroxide. What concentration of hydroxide is required to observe precipitation of magnesium, given that you have that concentration of magnesium? Okay, so in this case, if you solve for hydroxide concentration, then it's going to be equal to the square root of KSP divided by the concentration of magnesium. Okay, so that means concentration of hydroxide is going to be equal to square root of 206 10 to the negative 13 divided by the concentration of magnesium, which is 0.059. And this is a concentration of hydroxide equal to 187 10 to the negative 6 molar. So we can convert this to pH, no requirement, as just concentration of OH, that's fine. But that is the concentration of hydroxide that you need to precipitate magnesium. Okay, so that answers the question. But what if we extract a little more juice out of this problem? What if we ask what is the concentration of magnesium when calcium starts to precipitate? Well, now we have to calculate how much hydroxide you need to precipitate calcium. Okay, so the expression is similar. Okay, for calcium, KSP is equal concentration of calcium times hydroxide square. Therefore, hydroxide is equal to the square root of KSP divided by the concentration of calcium. This is equal to square root of 468 10 to the negative 6 divided by 0.011. Is that correct? Yes, 0.011. Okay, so the concentration of hydroxide to precipitate calcium is equal to 206 10 to the negative 2. So you notice that because calcium hydroxide is more soluble, you need a larger concentration, higher concentration of hydroxide to precipitate calcium. Therefore, you can see it this way. If you start increasing the concentration of hydroxide, magnesium will precipitate first. And once most of the magnesium precipitates, then calcium will start precipitating. So magnesium requires this much concentration, or this high concentration, 10 to the negative 6. Calcium will need a much larger concentration. Okay? So that's the first step. Okay? Now, that is the concentration of hydroxide when calcium starts precipitating. Okay? This is the concentration when calcium starts precipitating. Now, but we want to know what is the concentration of magnesium at that point. So, well, now we use that concentration to calculate the concentration of magnesium. So KSP equals concentration of magnesium times OH minus square. Now we are solving for magnesium. Okay? So in this case, concentration of magnesium is equal to KSP divided by OH minus square. And in this case, this is the one that we are using here. Okay? This is equal to 206 10 to the negative 13 divided by 206 10 to the negative 2 square. Therefore, the concentration of magnesium when calcium starts precipitating is equal to 485 10 to the negative 10. Okay? So the concentration of magnesium went from 0.059 to 485 10 to the negative 10 at the time that calcium started precipitating. Okay? So all around this selective precipitation is, what is required to actually observe selective precipitation. Remember, selective precipitation is precipitate something in the presence of something else that will also precipitate, but you don't want them precipitating at the same time. What do you need here? Well, you need to find something like, in this case, hydroxide, that will cause the precipitation of both, but that there are significant differences in solubility that allows you to completely precipitate one of the metals, in this case, before the other starts precipitating. So that's what you are looking at here. Something that will cause precipitation of everything, but the difference in solubilities are large enough that you can precipitate one in presence of the other. Okay? So that is all that you need to know about precipitation.